Hello, everyone, and welcome to the second episode in the ZK Proof webinar series. Can you all see my screen? I'm sharing a presentation. Michael, can you see? Okay, great. Okay, so as people are joining, and just to give us a little bit of context, I'm going to give you the background for this whole initiative. So who we are exactly? We are ZK Proof. ZK Proof is a global movement that brings together experts from all over the world, individuals and companies, with the goal of mainstreaming this technology of zero knowledge proofs. And together we want to build a standard that will allow this technology to be used by companies, by academics, by developers in the best way. And we know that to do that, we need a collaborative effort. And this is this initiative. We're doing many things in order to promote this. One of these things is guest blog posts. So on our website, you can find every couple of weeks a new expert giving some kind of like a walkthrough of key topics of zero knowledge. Our first blog post is already online. It's by Professor Dario Fiore. And our second blog post will be posted in the next week or so. And it's by Professor Justin Thaler from Georgetown University. And it's about interactive proofs. So this is all going to be on our website. Another thing that we're doing, that this is the reason we're all here today, is the expert series Fundamentals of Zero Knowledge, where experts are explaining the key topics and the fundamentals of this technology to allow people to get deeper into actually using it and getting into the practice of the technology. I'm already going to give you a teaser for the third webinar that's going to happen on the 16th of March. It's going to be a special webinar. It's going to be a live programming session. So instead of a PowerPoint, we will see basically the development console, and it's going to be led by Aurelis Nicolas from Kedit. So that's going to be in 2 weeks from now. Stay tuned. And and this are all we're doing as a lead up to our main event, which is a workshop that happens once a year. This time it's going to be in London in April, exactly in a month from now. And it brings together experts from all over the world to meet face to face to discuss the standardization proposals that we are receiving, and actually exploring them and developing them on dedicated working groups. So if you want to know more about that, also it's on our website. We have a early bird discounted tickets that's only until the end of this week. So without further, one last thing, this is just a brief about the speakers that we have, really the best of world academics in the field of applied cryptography. And now I'm gonna really start the session of today. The second webinar in the expert series of Fundamentals of Zero Knowledge, today led by Michael Riabzev. He's the co-founder and chief architect of Starkware, and is also a co-author of the Starkware protocol. So really the person to lead this talk today. And yeah, without further ado, I'm gonna leave this stage and give it to you, Michael.
Hello, everybody. Can you hear me well? Do you hear me?
Yes, I can hear you.
Okay, great. So let me just share the slides. Okay, hey everybody. I will talk with you today about introduction to the Stark proof system. Before that, I'll just say a few words about Starkware. Starkware is a company that uses proof systems to scale blockchains, to provide scalability and privacy. We plan to go live this month together with Diversify with a self-custodial and scalable exchange. More details in the presentation. We are a team of about 30 people, most of us are engineers, and we were founded with $40 million with equity and the grant from the Ethereum Foundation. So what we will talk about today, we will start with a high-level introduction to cryptographic proofs and a few examples of what they can be used for. We will see there what are the main features of the Stark protocol. We will continue with the special example of StarkX, the Stark-powered exchange that can be used to scale blockchains. And we will finish in diving into the Stark protocol, hopefully getting some intuition of what is the magic that is done inside. Please, if anybody has any questions, feel free to interrupt and ask me. I'll be happy to answer. I'll be more happy to know that I can answer a question than not getting any feedback from you. And it's much harder now in the webinar as I don't see the faces of anybody. So let's start with introduction to cryptographic proofs. So what do I think of when I think of a cryptographic proof? First of all, we start from a predicate that can be described using any program. I can think about a Python program or a C program that gets an input. I think of an input of pair X and W. X is I call it a public input. W is a witness. We will see exactly what is the difference in a moment, but technically we can think about it as a program that gets an input and outputs true or false. True, the predicate accepted the input. False, the predicate rejected the input. Using cryptographic proof protocol, we can compile this predicate to two executables. We can compile it to a prover executable and a verifier executable. Now, the prover executable, when it's provided a valid input X and W, it can generate a proof of knowledge, technically a proof of knowledge of a witness W, such that X and W satisfy the predicate, and the verifier can read the explicit input X and the proof pi, and decide whether it accepts or rejects this proof, whether it is indeed the case that the prover who generated this proof knows the satisfying witness to this predicate. Let's see a few examples of what it can be used for. So first of all, the most classical example for this is computational integrity. We can think about a delegation of computation to the cloud. This is something that we do a lot, but do we really trust the result that we get from the cloud? For simple computations, if we have no reason to think that the cloud provider would want to cheat us, it is probably okay. But what if I'm doing this very heavy, long computation that would take a long time to do, and I want to use the cloud resources, and the result of this computation would be initially whether I want to do all my operation over the AWS cloud or the Azure cloud. Maybe in this case, somebody in Amazon could notice that this is the computation I'm doing and would tamper my result. So we can think of this case of the following predicate. The public input to this predicate is a program and a value, an input value, and the result claimed by the cloud provider to be the result of the computation. The witness in this example is ignored. And all this predicate does is asserts that the result indeed equals to the output value of the program when it is ran with the input value as its input. Okay, this is just a general case of verifying the input. I know that if Amazon, for example, can generate a valid proof that would satisfy the verifier, then they could not tamper or cheat me in this result. Another example is the knowledge of a pre-image of a hash. I could think about a predicate that gets a public input X, which is a hash, and a private input, a witness W, which is a pre-image of this hash. It could be a file, I don't know, maybe a big movie or something like that. and it asserts that the hash of the private input is indeed the known input X. Notice that the verifier in this case only sees X. It does not know what W is. And in some cases, given the proof, it cannot learn anything about the witness W. This is the case of zero knowledge proof, and we will see it in a few slides. Another more general example to think something a bit different from the previous examples is chess. Let's assume that X is some state of a chessboard. And what the prover wants to show is that white always wins. The white always have a strategy to win. So W, the witness in this case, could be an explicit strategy for the whites. For every step the blacks do, what would the white do in order to win? So this is indeed a predicate that one can write a program to verify. And you can think about this non-trivial claim that the prover can prove that the white always wins for some state. Any questions so far? Okay. So let's continue to the specific proof systems called ZK Stark. So, and look at its attributes. So ZK is an acronym of, first of all, zero knowledge, saying that looking at the proof pi does not reveal anything about the private witness W. An interesting example for this could be a predicate showing knowledge of collision for SHA-2. We can think about the predicate that as a private input receives two values, verifies those are two different values, hashes them together, and asserts the hashes are the same. So one could satisfy this predicate if and only if they know a collision for SHA-2. And one could generate a proof in a zero-knowledge proof system showing knowledge of such a collision without revealing anything about it. For example, one who knows the collision could put such a proof on their website, and everybody would be sure that they found a collision to SHA-2, but nobody would learn anything about the collision, about those inputs. S states for scalability. Scalability says that the verification of the proof is logarithmic, or actually polylogarithmic, in the time it takes to explicitly verify the predicate. So it could be the case that the verification of the predicate is very long. For example, in the case of the hash per image, it could be the case that the witness is some very big file, let's say a Blu-ray video, that it took a while to hash. But the verification would be only polylogarithmic in the time that it took to do this hash, the time that it took to compute this predicate. So actually in the ZK Starks, the verification almost for every computation takes in the order of milliseconds. Transparency. Transparency, it means that in order to verify a proof, I don't need any trust assumption in any party. It means that if I go somewhere on the street and I just find the proof lying down there, I can read it and verify just a mathematical proof and be sure that it is sound, that it is okay. It is in contrast to other proof systems that would require a trusted setup, that if something leaked there or somebody tampered the setup phase, they could forge a proof to any statement. This is not the case in Stark. If you could generate a Stark proof, then you really proved the statement. You cannot just forge it. Argument of knowledge. Argument of knowledge, it means that the fact that a prover generated a valid proof that satisfies the verifier means that the prover actually knows a valid witness satisfying the predicate. This is important to show that we have here knowledge and it's not just a mathematical statement showing something is correct. For example, it could be the case that probably for any hash value, there is some pre-image. But the fact that a prover can generate a Stark proof showing they know a pre-image actually shows that they know it. It's not shows that there exists a pre-image, it shows they know it. And it is important, we will see in a few slides, that it is the property used in the construction of Stark exchange. Any questions so far? Okay, so let's see how we use the Stark proof system to scale blockchains. So first of all, what is the scalability issue that we have in blockchains? Blockchains are a great system for self-custodial value. When you really have a coin, for example, in Bitcoin or in Ethereum, it's really yours. It's not like in the bank that if I have money in the bank, it could be the case that I want to withdraw it and the bank tells me, no, you can't. Or I want to, the custody is actually in the bank. It's not the case in the cryptocurrency, if I really have the secret key. But there is an issue here with cryptocurrencies that if all the operations are done on chain, then you're really limited in the number of operations in each block. Means you're really limited in the number of operations per second. So there is there are exchanges over Ethereum that provide you the ability to exchange different coins. This is the main operation there, while you keep the custody for your funds. It is done using smart contracts. But in the naive approach, all the transactions have to be sent on chain. This really limits the number of transactions on chain, and actually such exchange can operate in the rate of about 4 transactions per second. What does it say? It says that if actually there are 5 people that want to send transactions in a second, the 5th person would have to provide higher fee in order to compete with the 4 that came before them. And of course, if you have more and more people, what would give a race of people offering higher and higher fees? I don't know how many of you are familiar, but for example, in the top value of Bitcoin, if in the end of 2017, if you wanted anybody, any miner, to look at your transaction, to consider putting it in a block, you had to provide a fee which was about $60. $60, 60. It's not something that you would go and buy in coffee with such a fee. So if we have low throughput, it actually leads to high fees. What we do in Stark Exchange, we will see the details in a few slides. We batch a few transactions together and we generate a proof of knowledge for those transactions, and we only update the state with a proof of knowledge of those transactions. So when we use batches of 4,000 transactions, we get to a rate of 550 transactions per second, which is already much, much faster than what the standard decentralized exchanges provide. But this is still not what classical systems provide. For example, Visa handles the rate of approximately 2,000 transactions per second. But as you remember, if you remember, in the Stark, the proof size and its verification is polylogarithmic in the length of the computation of the predicate. So it means that we can use even bigger batches and gain greater scalability. So if we do transactions of 64,000, if we do batches of 64,000, we get to a rate of 9,000 transactions per second, which is more than 4 times higher than what Visa handles, which means it is more than enough. And it is not a hypothetical example. We were already able to generate such proofs here in Starkware. I'll skip this slide. So what is the idea behind Stark Exchange? So in blockchain, we have a lot of nodes all doing exactly the same work. So if I send a transaction, I send it to the blockchain, and the miner has to verify this transaction is legitimate. It has to verify my signature. It has to verify I have sufficient balance, etc. After the miner is decided to put this transaction in a block, when the miner sends this block out, any node on the blockchain have to verify my transaction again. They have to do exactly the same computation again and again. And of course, this work is linear with the number of transactions that need to be verified. What we suggest is making one node working harder than the others, and all the rest being much weaker. So in Stark, we have a one node that can generate a proof, and this is what actually sent to the blockchain, to the standard Ethereum blockchain. And all the nodes of the blockchain verifying our transaction, actually verifying only the Stark proof of knowledge of those transactions. And as I said before, what we do actually is we batch a lot of trades together to gain this scalability. So let's see an example of the architecture that is done here. So the StarkX engine is actually a backend of exchanges. We plan to go live with Diversify this month. So the exchange would be Diversify in this case. And we have on-chain a Stark verifier contract, and the main contract called the Stark Exchange. So the balances of the users are all kept in a Merkle tree, actually in the leaves of the Merkle tree. And the thing that is written on-chain on the Stark Exchange is only the root of this Merkle tree. So when two users want to trade, they send orders to the exchange off-chain, just like using a centralized exchange. The exchange matches the orders together and sends us the settlement. We get a lot of such settlements, and we batch them together. And what causes the root, of course, to change because the balances are changed. We send the proof of knowledge of transactions changing the state of the tree from the previous root to the new root, to the Stark verifier. The verifier verifies this update is indeed legitimate and updates the exchange state with the new root. Does anybody have any question they would like to ask before I dive into the Stark protocol? Okay. So let's dive into the Stark protocol. So just like other protocols like the TCP/IP protocol, it might be comfortable to look at the protocol as a stack. So in the highest layer of the stack, we have the statement. The statement could be the knowledge of transactions changing one root to another, or it could be the knowledge of a strategy for the Y to wins, etc., etc. This is exactly the examples we have looked at before. What we do with this statement, we do some localization step that we will dive into in a few slides. We do an arithmetization step after that, moving this localized language or statement to some more algebraic statement. And after that, we go to low degree testing, which both the arithmetization and the low degree testing does not, the intuition here is not clear from just looking at the stack, but hopefully when we dive into the different steps, it will be more clear. And eventually what we do is a realization using Merkle commitments. So what we will do now is we will start with a suggestion of an implementation of a protocol for computational integrity for this statement layer, we will see where the issues are. We will go down the stack to the lowest layer, to the low degree testing and the realization, and we will see an independent solution that can solve the issue in these layers. And we will gradually go from up down and from down up and meet in the middle to see what exactly the Stark protocol is. It's some layer in the middle. Okay. So we will start with the highest layer. So we have a predicate. And as we said before, we can compile it to a prover and a verifier. It could be executable. The prover just runs the predicate given an input. And what it could do, it could just generate the execution trace of this predicate validation. What could the verifier now do? The verifier could choose randomly a pair of two consecutive rows in this trace and to check if they are indeed valid, right? If we think about a specific architecture, for example, an Intel architecture, given a state of all the registers in one state, we know what would be the next valid state. So we could think about the verifier doing exactly this validation. And now the question I would like to ask, and here I would like somebody to answer me, is what's the issue here? What would be the probability of a prover to cheat if a prover wants to? Would anybody want to say anything? Do you hear me?
Yeah, I think there are some questions on the chat, Michael.
Oh, so I need to find where the chat is. Okay. So just a second. Okay. Yes. Okay. What about data availability? Okay. So just a second. I'll talk about data availability. Yes, the root changes is and maybe in every block. I believe the root changes once in every block. Okay, so I see, Leslie, you talked about Stark X, right? So let's see. Leslie, you asked what about data availability? Yes, so about data availability, why do we actually need data availability? In the construction I've just described here, the users can always be sure that their balances would be tempered and the exchange cannot steal money from them, and that the exchange cannot just change any balance, because they always have to provide a proof of knowledge for valid signed transactions changing balances. But the exchange could do a different attack. The exchange could decide they are not serving the users anymore. And in this case, I could say for some user that I see that has, for example, 100 ETH in the bank, in the account, that if they want to withdraw it, I would like half of it. Otherwise, I'm withholding it in the exchange. I would not be able to use it, but I guess this user would prefer to withdraw it and give me half. This is just some ransom attack. So what we have in this case is the escape hatch, where this user can ask the StarkX contract to force the exchange to withdraw their funds by putting a request with a time lock to withdraw the funds from their balance. If the exchange does not satisfy the request within a week, the user can call the contract again, and to show it that they asked to withdraw the funds, the exchange did not serve them, And now what the contract can do is to freeze the exchange, actually to freeze the Merkle root in the exchange and not to allow any more updates. In this case, the users should be able to withdraw their funds by showing their balances and authentication path to this root. If, first of all, before I'm going to this malicious scenario, if everything is okay and the exchange is trustworthy, then the users can just ask the exchange what are their balances and it can tell them. And if the users want to verify their balances are consistent with what is written on chain, they can ask the exchange to get their authentication path and they will verify it. But if the exchange becomes malicious, then now they have to compute somehow this authentication path. So if the exchange is not trustworthy anymore, what they can do is ask it from our committee member. So the committee is something used in StarX exactly for this scenario. A committee is a group of reputable companies that all of them hold the state of the exchange as well. Moreover, whenever we send a new batch and a new root to the contract, we have to provide to the contract enough signatures from the committee showing the committee members actually know this data. And in case the contract does not see enough signatures, it would not update the on-chain root to the new one, ensuring enough committee members always know enough data. So if the exchange becomes malicious, the users can get their authentication path from those committee members, or those committee members could just publish all the information for the users to use. So does it answer the question about data availability? So yes, you have to trust the committee. Prove that the new, so I'll just read. So I have to trust the committee, say that the exchange and the committee lose the data. Then you have a proof that the new state is valid, but you only have the state root and not every value correct. What would you do in such a scenario? Yes, in case both the exchange and the committee members lose the data, then yeah, it is indeed a problem, but it's not more the probability of this scenario is not actually much higher than my bank losing all my data or some other centralized party. Given frequent updates, I think yes, it could be the case, but I don't think. Yes, it is the case that if everybody loses their data, then the data users might not be able to withdraw. Does it answer the question? Great. So, sure, you're welcome. So let's continue with this. So what I suggested before was for the prover to provide the verifier with access to the execution trace of the predicate given as input, the valid, the satisfying witness and instance. And the verifier could just check 2 consecutive lines and verify they are consistent given the architecture. What would be the issue in such a case? Does anybody have an idea what would be the issue in this? What's the issue in this case? What's the probability of a malicious prover to cheat? So the probability in this case of a malicious prover to cheat would be approximately 1 over the length of the trace. So assuming the trace is very long and the prover, the malicious prover, only changes 1 line in this trace and actually splitting this trace to 2 separate parts, where the upper part is consistent with itself and the lower part is consistent with itself, the probability of the verifier to catch exactly this split place is very low. It's 1 over the length of the trace, which is not good. So now we will continue from the lower area of the stack, low degree testing and realization. And we will do it with a story about Alice, Busy Bob, and Charlie the coder. So Alice is a manager. She's asking Busy Bob to compute the square roots of a few numbers. But Bob is very easy, and the issue is that there are many numbers. 2 to the 50 numbers, it's a lot. It would take Busy Bob a lot of time. So Alice doesn't even provide Bob the numbers explicitly because it's a lot of numbers. She just provides him with a Merkle root of those numbers. And Bob can use this Merkle root to download them, for example, from BitTorrent. BitTorrent uses Merkle roots to verify the consistency of all the slices, so Bob can use it as well. But what Bob could do, because Bob is very busy and Bob doesn't even have time to download this file. So Bob hires Charlie the coder to help him compute the square roots. But there is an issue because Charlie might have bugs. And it is very important to Bob to verify that the work is indeed done correctly. How could Bob do that? So Bob has a very weird idea, but it might work. Let's follow it. If you want to understand the idea behind Stark, I really suggest to concentrate on the few following slides. It's about, I don't know, 5 minutes. But this is actually the magic that happens in Starks. So Bob asks Charlie to think about the input as values of a polynomial. So it actually, what Bob asked Charlie to do is to interpolate a polynomial such that P of I is equals the ith number Alice provided. And Charlie can do it because it's interpolation. It's approximately efficient algorithm. So what we should notice here is that the degree of the polynomial that Charlie would gain is lower than 2 to the 50. This is an important property of this polynomial. And this polynomial actually represents the values Alice asked Bob to work on. Bob would ask Charlie to do the same for the results that Charlie would get. So Charlie would get the square roots of the numbers, and Bob asked Charlie to represent them using a different polynomial g, on such that the equality that g in I is always equal to the square root of the ith number. And we should notice that the degree of this polynomial is, again, lower than 2 to the 50 because it's the result of the interpolation of 2 to the 50 points. An important observation here is that the polynomial q defined as the difference of g and p squared must vanish over every x smaller than 2 to the 50. And the degree of this polynomial is at most 2 to the 51, because it's a sum of two polynomials, one of degree 2 to the 50, and the other one is 2 to the 50 squared, so the degree is at most 2 times bigger. An algebraic fact that I guess you're familiar with is that R is a root of a polynomial if and only if the polynomial x minus r divides polynomial q, meaning it can be factored to a product of some polynomial b of degree smaller than the degree of q, and the polynomial x minus r. And inductively, we can show that q would be a valid polynomial if a requirement is that q is a product of some polynomial b of low degree, of degree at most 2 to the 50, and the polynomial and the simple polynomial vanishes over all the values from 0 to 2 to the 50. Any questions about these slides, about the math here? Anything? Okay. Okay, so what would be the test that Bob will do? How could Bob verify that Charlie did the work properly? So we have here the facts below. The three higher points are actually the parameters that we described in the previous slide. And what would Bob do is draw a random R between 0 to 2 to the 60. The domain is bigger than what we had before, and would just verify that G in R minus P squared in R equals to B in R, another polynomial that Charlie should provide, times this vanishing polynomial. Let's see, first of all, notice that this test is very efficient. If before, if before the options of Bob would have been to compute by himself, which is very expensive, or to verify Charlie's result explicitly by going over 2 to the 50 numbers and squaring them, now the test requires only drawing a single point and reading 3 values from what Charlie have computed and putting him in this simple formula, much faster than 2 to the 50. This is actually one of the properties that shows how you can scale using Starks eventually. So let's analyze this test. In case Charlie did a good job, then Bob should be always satisfied, right? Because in this case, the difference indeed vanishes over the domain of 0 to 2 to the 50, and in this case, Charlie should be able to find a polynomial b, and this equation should hold. But what if Charlie failed? So if Charlie failed, we can notice that by definition, both the sides must be of degree at most 2 to the 51. And if they are not equal, they could agree only on at most 2 to the 51 points, because two polynomials of degree at most d, if they are different, then their difference is of degree at most 2 to the d, at most d. And if they were different, then their difference is not the zero polynomial, so it could have at most d roots. Those are exactly the points they agree on. So they could agree only on at most 2 to the 51 points, but the test, the domain that Bob sampled R from is much bigger, is 2 to the 60 points. So the probability of Bob sampling a bad R value is very low, is about 1 over 500. And if it's not sufficient, Bob can do this test a few times, 2-3 times, and the probability of Bob choosing in all cases bad values of R goes down exponentially. Any question on this? Okay, so before we thought about the case that Charlie the coder only does mistakes. There could be a bug, and we provided a protocol for Bob to verify Charlie did a good job. But what if Charlie the coder is malicious? Maybe Charlie is lazy, and Charlie would only like to provide Bob something that would satisfy him, and not actually do any work. So in this case, Bob could ask Charlie not to answer interactively to the questions just by evaluating the polynomial, but in advance evaluating all the polynomials over the domain of 0 to 2 to the 60 and commit to them using a Merkle tree. Now Charlie can do this, now Bob can do the same test, but whenever Bob asks Charlie a value of the polynomials, Bob would ask Charlie to provide the Merkle authentication path to show that this value is indeed what Charlie have committed on. This prevents an adaptivity from Charlie. So Charlie first commits on values, and then Bob verifies they are consistent with the test above. And Bob, additionally with this, Bob can verify that the part, the segment of the Merkle tree that is consistent with the input is indeed consistent only by looking at this root. And similarly for the output, it can just provide Alice eventually the Merkle root of the outputs, and Alice can download them from BitTorrent, for example. And Bob would actually never download any such big file, would always be very succinct. But there is another issue here, because the test, the soundness of Bob's test required both sides to be low degree. But if Charlie is malicious, Charlie could somehow cook the values, these evaluations, to satisfy this equation with high probability. But in order to do it by the analysis we did before, those evaluations could not be low degree. So low degree testing is a way, is a protocol for somebody succinctly to ensure some evaluation is very close to be a low degree polynomial. So this is another protocol which is not described in these slides, where Charlie can prove to Bob that those values he committed on in the Merkle tree are consistent with polynomials of degree at most 2 to the 50. Okay? Any questions so far? Okay. So now we've seen this story and the idea of how arithmetic construction, algebraic construction can be verified succinctly. So we'll go back up the stack to see how we can take our localized construction from before and get it closer to something algebraic. So before, remember what we did? We thought about the prover providing an execution trace and the verifier just to choosing a pair of consecutive rows and verifying it explicitly. And as we said, the way it could verify it is using, for example, the CPU architecture used to execute this program. And what would be this architecture? This architecture is actually the spec of the CPU in this case. And what is the CPU? The CPU is actually a circuit. So the idea that we will do, we will arithmetize this circuit, this transition function circuit, right? The CPU is not a circuit of the entire program as done in other cases, in other proof systems that, as the Snark, etc. Here the circuit is only the transition function from step to step, and we will arithmetize it, and the trace should be arithmetized as well. And eventually what they will do, then as in the story of Bob and Charlie, Charlie generating this trace would compute a low degree extension of this trace, and the arithmetic circuit will be used to verify it. So how can we arithmetize a circuit? So actually, it's a construction well known and very simple to take a Boolean circuit and to arithmetize it to a polynomial that over the input of zeros and ones. So this is a naive way that can work. If you want to actually generate efficient proof systems, efficient constraint systems, you should do something more clever and more sophisticated. But I will not go into this in this presentation. If you want, you can ask me about this later. So now we can finish in this meet in the middle and to see what exactly the Stark protocol is, just to wrap up all these parts that we have seen. So in the Stark protocol, we would like both parties, the prover and the verifier, to agree on some arithmetization of this transition function. And it implies arithmetization of the trace. We would like the prover to compute the trace, to encode it in the arithmetic form, and to do a low degree extension to it. As we see in Bob's and Charlie's story, Charlie took something that was 2 to the 50 numbers, but before committing to it, he computed its value over 2 to the 60 points. This is a low degree extension. And we finish by using the same technique as Bob and Charlie did to verify succinctly that the trace, this arithmetic encoding of the trace, satisfies the arithmetic form of the transition function, saying that every 2 consecutive states in the trace satisfy the transition function. So this is actually it. This is the Stark protocol, and those are all my slides here. I'll be happy to take questions if you have any. Okay. So thank you. Anybody here? Yeah, will the slides be available? Yeah, no problem. I can just give you a reference here.
We will also share the slides and the recording. But if anyone has a question for Michael, this is really a good opportunity when he's here live. So really don't be shy. This is why this platform is for.
So maybe I have a question, maybe not necessarily technical, but you mentioned that Starkware is going to go live this month. So I'm wondering if you have maybe a bit more details about that, since it's probably one of the first times that Stark is going in production.
Yes, that's
and also, I believe that there was an announcement that the prover is going to be open sourced. Could you also say something about that?
Yeah, sure. So Starkware will be live this month together with Diversify. Diversify is a self-custodial exchange that currently uses a contract with all the transactions implicit on chain. And we will be powering it to provide it scalability and super low fees for their users. This is about this. About open sourcing, so Starkware will publish a code for the Ethereum Foundation of Prover and the Verifier in C, showing the statement of hash chain. This should be available in a few months as well.
So it's only one proof statement and not like a generic prover?
Yes, that's right. This can be used as a reference, but yes, this is tuned for best performance for a specific statement.
Nice, thanks. And thank you very much for the talk, by the way, very, very interesting and very clear.
Okay, thank you.
Yeah, thank you, Michael. Anyone else wants to ask a question? So
I see Cindy have a question, and Yash asked, what are the differences between a Starkware Zero Knowledge Stark-based DEX versus Loopring's ZK rollup DEX? Okay, so there are a few differences. First of all, So I answer Yash first, and then I ask Cindy what's the question. So Yash, about your question, Loopring is using Snarks and not Starks. So it has the advantage. First of all, Snarks has the advantages of having smaller proofs and less gas consumption to verify them. This is the advantage of them. The disadvantage of Snarks is that it requires a trusted setup. I'm actually not sure who participated in the ceremony Loopring did when they started their exchange. But as I said before, it is the case that if I am doing a setup for a Snark statement, for some Snark proof, and I'm generating the proof for it, I could, if you can't trust me to not get any information from the setup, in the setup phase, there is some random parameters that if somebody can read them, they could forge a proof to any statement, even false statements. So if I just want to generate a Snark-based system without doing a good trusted setup, which is what is a good trusted setup is a good question, because it's not something that is well cryptographically defined, because in a way trusted setup, as its name applies, it means that you have to delegate the trust to people. You can't anymore just read the cryptography, read the math and understand it. You actually need to trust the people not to do something bad. But if somebody would want to do something bad, then they can forge a proof to any statement. So this is one big difference in between the two approaches. Another difference, not about the proof system itself, but about the construction, is that Loopring is putting the data on chain. So as I explained before, in Starkware, to provide great scalability, we don't put data on chain, but the data is off chain, verified with the committee, which could be thought as a small and permissioned blockchain. This allows us to generate batches as big as we want, not limited by the block size. But as was mentioned before, in case both Starkware, Diversify, and all the committee members lose the data, we all together decide to be malicious and collide and we're turning bad, then it could be an issue. And when the data is on chain, then anybody can be sure that they can use this data to withdraw their funds. But of course, putting the data on chain limits each and every batch with what you have on chain. Another big difference between Loopring and Starkware, and this is again going to the difference between Starks and Snarks, is that in Snarks, the proof is circuit-based. It means that for any different circuit, one has to generate a new trusted set of parameters. There are some universal circuits, but as much as I know, their efficiency is much lower. So I'm not sure exactly if Loopring using a universal circuit, but if they are not, then they are in the case that or they have to generate a trusted setup for each batch size they are planning to send on chain, or from the other side, they are just limited to a specific batch size and they cannot go, first of all, above it. But if they have some low rate, they always have to fill this batch with, I don't know, dummy transaction or something like that, because the circuit requires some fixed size. This is my understanding on the differences there. So I see a question from Cindy. What it be possible for the exchange to front-run users? Yes, the exchange able to front-run users. So the only thing protected here with cryptography is the balances and the fact that they cannot be tampered, and that anything can change only if a user signed on it. But all the matching engine and the order handling is done technically by a standard exchange, and this exchange technically can front run user just like any classical system, classical exchange. Could you say something? So Sky asks, could you say something about censoring, withholding, front running? Okay, so as I said before about front running, the exchange technically can do it. There is no cryptographic enforcement that would not allow it. About censoring, so we have the escape edge mechanisms that are actually anti-censoring mechanisms. So as I explained before, if a user wants to withdraw and ask the exchange using the off-chain interface to withdraw and the exchange would not serve them, the user can ask it from the smart contract, and after a time lock, if the exchange would not serve the user, the exchange can freeze the contract. There is another scenario. This is only if the user has funds on off-chain. In case the user has some funds on-chain, for example, the user only deposited but the exchange would not take this deposit to the off-chain area, then the user can again ask to take the money from it, and after a time lock, the user can take the money to themselves. I'm not sure about what do you mean by withholding. If you can write about it, but I'll continue with the question. Also, if you improve scalability, this is practically bad for a business model of miners. Transaction cost goes to zero. Is this something you take into consideration and have an opinion about? So I have an opinion, but it is actually the other way around. So this is only my opinion, what I'm saying now, but I think that cryptocurrency is in a bit of trouble now. So in a way, its name says that it is a currency, but it is actually cannot be used as a currency. It is more used like an investment right now. And I understand why, because in Bitcoin, if I'm not mistaken, for example, you can do about 7 transactions, standard transaction, the thing that it is built on per second. In Ethereum, it's about 14 transactions per second. So if I would like to use it as my main currency and try to buy coffee with it, and we have, I don't know, more than 20 people in a second in the world trying to buy coffee, they would start to compete, providing higher and higher fees. And of course, if those people that want to buy coffee are now competing with people who are buying, I don't know, furniture, televisions, cars, houses, then of course the fees that they can provide are much, much lower than what somebody who buys an apartment. So eventually I could not use right now cryptocurrency as a currency, or maybe I personally can, but it cannot be something very common. I believe that using systems like this that provide scalability to blockchains, cryptocurrencies can actually become a currency. You can do unlimited transactions per second, and you can go and buy coffee. And the best thing here is that it is the opposite. The more people using the system now, the fee per trade, the fee per transfer becomes lower, because remember, the proof size is logarithmic, which is approximately constant technically. It doesn't change much. So if we have, I don't know, 10 people in a batch, each of them would pay about 1/10 of the cost of sending this proof on chain. But if we have 1,000 people on chain, 100,000 people in a batch, then each of them would pay a much smaller fraction of about the same amount. So we have here something really, really awesome, which is the economies of scale. So I believe I believe this scalability would actually be better for miners because it would probably, so I believe this is just my thought, it would probably make the network much more usable and much more people would like to use this currency. And I believe this could make the value of the value of the currency they are mining higher. This is just my thought on this. Let's ask, how large are the StarkDex proofs? Is there a difference between the size of the proofs for 4K batches and 64K batches? So the difference is really minor. It scales logarithmically for, I don't sure about 4K batches. I can say that for 1K batch, the proof size is about, I don't remember the proof size. What I actually measured recently is the gas cost when you send on chain, which is the proof size plus the computation, was about 4.2 million. And when you go from 1K batch to a 64K batch, it grows to about 4.8 or 9 million, something like that. So you can actually feel you're actually not limited anymore by the block size. About the proof size, it is about 40 or 50K kilobytes, something like that, but please don't catch me on this word. That was, thank you, Yash. Okay. Cindy, it means more the apps will be possible with lower TX costs. Cindy, would it be possible for the exchange to front run? Cindy, I'm not sure, is it a question? It means more the apps will be possible with lower TX costs. Okay, it is just a statement, I guess. I was answering, okay, on minor fees. Okay, yes, I agree with you, Cindy. How could you mitigate front running with the StarkDex down the line? So it is possible to add to the proofs, to the statement, information about the matching engine. It is possible for each and every statement. One of the issues here is that I think the statements of the matching engine is something that exchanges actually change for pretty frequently. They add support to new type of transactions and new algorithms to do matching. Of course, it could allow front running. They could introduce an algorithm that does front running, but I think they usually add some enhancement and improvements to their matching engine mechanism. In case you add it into the cryptographic proof, which is verified on chain, it would be much, much harder to do such updates. So the focus of StarkX is to preserve self-custody, but it does not prevent front running. But yes, it is possible to prevent front running using StarkX if there would be some exchange that can commit for a very specific strategy, matching strategy, and they can be sure that it is rock solid and they would not want to change it, I don't know, in the next year. Because of course, any such cryptography is something very delicate and you don't want to change frequently. For example, in the StarkX system, it could be the case, we are preparing to the case that if somebody would need to update something about supporting something newer or updating our statement, it would be possible using an upgradability mechanism, but this upgradability would be a very, very long process. We would first have to provide the new code out and to convince everybody it is legitimate. And then we can put this code on chain, and the contract enforces that we cannot update anything or change anything in the logic of the contract for a long time of more than a month, to make sure that anybody can verify it and agree with it. And in case that anybody thinks that there is an issue with the new implementation, they can just get out of the exchange. So while this is okay for self-custody, to make sure that no balance is changed unless the user is signed on it, I believe it might be harder for matching engines. Does it answer your question, Cindy? Okay, great. Any more questions?
Okay. Michael, thank you so much. It was really an amazing presentation. I think everyone here gained a lot from that. So really thank you for giving from your time and knowledge to show us this. Everyone else, thank you for joining. Please stay tuned for the next webinars. I will also send you a feedback form right now, and it will be really great if you can give us the feedback so we can know how we can make this thing better for the community. And everyone have a great rest of the day, wherever you are.
Thank you.
Bye.
Thank you, Michael.
Bye.